it's me, Michelle. Today's video is going to be on nuclear decay calculations.
So let's have a look again at nuclear decay. Here we have our familiar expression that the parent material at any time will be the parent material at time 0 times 1/2 the power n, where n we've agreed is the number of half-lives, or if you like we can make n out of y and l. Let's let y be the time elapsed and l the duration of one half-life, and that means getting p over p0 we can have here the fraction of the parent material that is remaining. So that's a relatively straightforward application, and here you'll see that the fraction is 1/2 to the power y over l. If we take logs, we can get the log of f equal y over l times the log of half, and thus solving for the age of this sample here, we can get y is equal to l log f over log of half, and solving now for the half-life, we can get l is equal to, the half-life equal to, a y, the age times log of half over the log of the fraction remaining. So here we have the age of the sample and the half-life, and above here the fraction remaining. These are the three expressions we need in order to do nuclear decay calculations. Let's put them to use here and see if we can solve a simple example. Our goal here is to have a look and try and see what's going on with this unstable isotope. We have 20 grams of it present at 1 p.m. and later at 3 p.m. we find 15 grams of it. So our first question is, what's the half-life of the sample? And in order to solve that, we'll just go and get our half-life expression from above, that L, the half-life, is y, the age, or the time elapsed, times a log of half over log of the fraction remaining. Putting in here y, the time elapsed, 2 hours between 1 and 3 o'clock, now the log of half, and dividing now by the log of the fraction of the parent material remaining, which is 15 out of 20 grams are remaining. You can see that this comes out in units of hours, and the half-life of this sample is 4.82 hours. Here's another question. When will 10% of the parent material remain? So now we have to solve for, given a fraction, solve for the age of this sample, and we'll do that here by using our expression for the age of the sample, y. So y is equal to L, the length of a half-life, times the log of the fraction remaining, divided by the log of half. So that's 4.82 hours, the half-life, we just determined it above, times the log of 0.10, which is 10%, divided by a log of half here, and we find out that this is 16 hours. And so if you started at 1 p.m. and you add 16 hours to that, I think you wind up at 5 a.m. the next day. So by 5 a.m. the next morning, we would expect us to have 10% of the parent material remaining. Let's put these ideas now here to use and solve a couple of other expressions. The first question here talks about the half-life of lead being 30.4 years and leaving a 74-gram sample to sit for 102.3 years. So what mass will remain? So Colin rightly suggested we solve for the fraction remaining. We'll do that. F is equal to half times half to the power y over L, which is half times age, 102.3 years, L, half-life of 30.4 years, and we get the fraction remaining as 0.0970. So 74 grams times 0.0970 is 7.181 grams, or just 7.2 grams in this question with 2 sig figs. So we would expect after 102.3 years just to have 7.2 grams of that isotope of lead. The second problem is looking about polonium-210. Its half-life is 3.1 minutes. And if we were to leave this 140 gram sample till 11.3 gram remains, how much time has passed? We're going to solve for the time elapsed, or the age, it's y. You saw it in the example above, so y is equal to L times log of f over log of half. So L is the half-life, 3.1 minutes. Log of the fraction remaining, 11.3 grams now, 140 grams initially, will get us their fraction remaining. Divide all that by log of half, we get 11.26 minutes, or to 2 sig figs, 11 minutes. Third sample problem, we have the 260 gram sample of some isotope that decays to 16.25 grams in 26.8 days, and we're trying to determine the half-life. So we'll here put in the age, 26.8 days, the log of half, divided by the log of the fraction remaining, which is, again, 16.25 grams remaining of the original 260 grams we had. Check that the units here will come out in days, and the length of one half-life here is 6.70 days. So really, that's it. 3 expressions which you just solve. That's about all for these calculations anyway right now, and you'll see that we can use them in many interesting ways in the future, but certainly this is the basics. Anyway, see you soon, everyone, And do be sure to check out the next 2 videos in our playlist for more. And stay tuned for our next lesson, Lesson 30, Binding Energy and Nuclear Stability.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!